谢谢。
Good morning. Very nice to be and address this group again. I hope you appreciate the short break. So yesterday I had an opportunity to focus on lessons learned with a special emphasis on our Ivanpah project. My topic today is Power Tower Solar Field Technology and Innovations for Optimization and Cost Reduction. And in my comments, I'm going to focus on some of these advanced and next generation technologies which have been informed by our experience, certainly at Ivanpah, but also all the projects that we've been working on. So the topics that I'll be covering today here are the solar field software that we have and use, in talking about some of the upgraded features. I'll describe the lower cost heliostat design. I'll also talk about the solar field integrated control system and the expert system, which is a new feature that we've recently added. I'll go into detail about the wireless solar field network. I'll also discuss receiver coatings. And then finally, I'll talk about molten salt at our solar energy demonstration center. Oftentimes, I believe this is one of the most overlooked characteristics, I should say, overlooked elements of good solar field design, and that is the ability to work with the existing landscape. So what we find is that our software enables us to actually provide flexible heliostat placement that allows us to work with existing terrain while maximizing energy output. We also have the ability in these solar fields to create do not disturb zones to avoid sensitive habitat or pre-existing structures that must be avoided during construction and during operation. It's also worth noting that the software allows us to accommodate terrain with different slopes. In the case of Ivanpah, we accommodate slopes of up to 6% grading. If you then look at the challenge we are presented with for Ashalim, you can see that we're using these optimization algorithms to determine the placement of the heliostat. And it's this type of software that actually allows us to use irregular sites, because oftentimes it's not possible to find symmetric layouts. And so in this instance, we were provided with this land identified by the government and said, make it work. And so it's this software that allows us to do this optimization. I'll also note that in the software, we're able to track tens of millions of components, right from drawing all the way through construction and operation for tracking. So it provides a complete cradle to grave view of all the elements inside the solar field. And what you'll see here is an example of Ivanpah where, although it may not appear, we create driving zones. So we anticipate the maintenance requirement, and that is accomplished by turning the heliostats to a vertical position to allow small vehicles and cleaning equipment to traverse the area out into the field. Of course, there are many benefits to looking at this, and the benefits of optimization really are around that the receiver here is seeing what appears to be a flat surface. So in this instance, the receiver is looking north at noon, and it's important to know that all of the optimization is done from the perspective of the receiver's viewpoint. So although you saw space in the previous slide for drive zones, this is what the receiver looks like if you're standing at the top of the tower and you look out to the north. So why do we do this? Well, here's the view from the south on an afternoon. And that is because an optimized solar field will yield 10 to 15% more energy per square meter. And so when you're in a constrained area, this allows you to increase your output or alternatively, for a given area, you can achieve quite more. Now, we talk a lot about the benefits of lower cost heliostat design. This is the second item on the agenda that I identified. And what we want here is minimal steel loading. We want installation that requires no site grading. So you'll note that that's the natural terrain. We didn't grade, we didn't level, and those heliostats are placed exactly 2 meters into the ground, and we have a GPS coordinate on top so that we always know the X, Y, Z coordinates. And we use that information as part of the software I'll talk about in a little moment. Given the distances to the tower, which you can see in the back, we actually have different focal lengths, categories of focal lengths, depending on the distance. So at 1,000 meters, or 500 meters, or 250 meters, we categorize, and that focal length provides greater precision that you'll see how we use that here in just a moment. Now, there's been a lot of talk about industry designs and heliostats, and there are different viewpoints. In the upper right corner, you'll see the Ivanpah heliostat, consisting of 2 mirrors. They're mounted on a harness in the back. You'll also see some spacing there, and I draw your attention to that to show you the difference between that and our next generation. There are companies that use very small, they're medium, and they're very large. But what I would say here is that the goal is to strike a balance between optical efficiency, solar field cost, including maintenance, because heliostats require maintenance, whether that is the equipment or the communications unit or the power connections. A large unit, here we can access this from the ground, which is considerably less expensive than requiring very tall equipment that sometimes actually can get stuck. So maintenance in the solar field is critical. Low-cost maintenance, I should say. If the heliostats are too small, as you heard yesterday, sometimes there'll be too many drive systems and many controllers required. And likewise, larger heliostats require more expensive structural support. Heliostat design also impacts the construction time, as well as ongoing operation and maintenance. And so here it was 15.2 square meters, and just for reference, that at Ivanpah, each heliostat provided 2.2 kW of energy, almost enough for one home, an average California home, in 1 year. So that's how we think about that. Now, this is important, is the heliostat installation. And all these pictures are a little skewed in the final report. You see how they are. So we developed this, and here you see that the pylons, the poles in which the heliostats sit, are put into the ground using a low-impact pylon driver. And this process eliminates the need for foundations and concrete pads. And so they're designed to operate and preserve their integrity, structural integrity, for at least 30 years. But importantly, this process promotes natural draining and avoids corrosion. Let me explain why. In the background, you'll see a mountain. Although Ivanpah is in the desert, it gets rain fairly frequently. And when the rain comes down the mountain, it rushes across the flat area down that 6-degree slope I mentioned, and it can be quite fast. When we were in construction, 3 months into it, we had a 70-year flood, which means the amount of rain that came down and the flooding would be expected to happen once every 70 years. And so, in fact, the pylons are designed to withstand up to a loss of 1 meter of soil around the bottom and still maintain their structural integrity. The benefits of this approach, as I said, are they minimize grading and leveling, which saves money. We maximize the retention of vegetation and natural features. Let me explain why that's also important. You heard yesterday concerns about reflectivity. It was a question I think I was asked at the end of the presentation. And by maintaining the natural vegetation, you minimize the potential for dust, since the crust of the soil remains and the vegetation holds that in place. So we see less dust at Ivanpah because we're maintaining as much as possible the natural contours. Although where it is close to the tower, where we used it for a laydown area, it's actually what they call bladed and graded, which means that it's rocks and it's smooth. But that's only near the tower. When we put this, we have this drilling where we auger, it's called augering a hole, and we vibrate, we loosen the soil and then vibrate down. Each hole is drilled exactly 2 meters deep from the ground, so that's why you'll see heliostats can have different heights as you look at them, but they're always two meters into the ground. But that loose soil is in place, and then we have this equipment that will pick up another tool and then insert the pylon. In this case, we vibrate it down. It was a vibro hammer, and so it holds it in place, and we have some stabilizing fins that keep it from moving. But here, no concrete was needed because the vibration packed the soil tightly around the finned pylon. You can't see the fins here, but they're there. So for Ashalim, this technique was different because we find that we always have to optimize, or rather adapt for the local soil conditions. So at Ashalim, we have a much looser soil, a lot of sand on top. It's a different type of desert environment. And so again, we're able to accomplish this by inserting a certain amount of grout inside the pylon, which provides the necessary stability. And so here you can see what that looks like in the next picture. So here's Ashalim, and you can see now the new heliostat design has eliminated the space. This is actually 4 glass panels. This new design, I'll just mention, has fewer components, so it also means easier assembly. So this is different. It's less expensive and yet stronger. The lower cost is easier to install. It is 25% larger than the Ivanpah heliostat, or it's 4 by 5.2 meters. So to give you a sense of what that is. The new design and the way in which we operate now allows full freedom of 360-degree positioning. It's also self-powered. And later on, you'll see a little more close-up image of that, but it's self-powered. Again, the topography is maintained here, and you can see that, again, the pylons, and then here's Ashalim during construction, and the rains came, and you can see the water, but again, those pylons are designed to withstand the occasional rain and sometimes even snow that we find out in the desert in Israel. So the third sort of element here is the Sphinx, or the solar field integrated control system, and the expert system. And the Sphinx gives you a sense because the job of the Sphinx is to manage the distribution of energy across the surface of the solar receiver, and it does that using real-time heliostat aiming and closed-loop feedback. Inside the solar field, we have on-site weather systems. We have visual and infrared cameras that provide real-time feedback into the advanced algorithms for solar field management. We also have proprietary optimization and control software to help maximize project performance and power production efficiencies. And also valuable is, I mentioned, the expert system, which analyzes this data in real time and then provides recommendations to both the Sphinx and to the control operator about what steps they may want to consider in the face of changing conditions. And that could be weather, it could be movement of cloud cover, but nonetheless, that system there is designed to help benefit the operator to ensure continuous optimal production. So here's a picture of the Ivanpah solar receiver steam generator. It consisted of 3 components. Each section, we had in the center a steam generator, and we're providing, as you can see, 600 kilowatts per square meter for the steam generator in the middle. So 600 kilowatts per square meter in the middle. On the top is the superheater, the very top. And that superheater is maintaining, the system maintains 300 kilowatts per square meter. And at the bottom is a reheater, which is maintained at 150 kilowatts per square meter. And so all of this and the responsibilities for each square meter is assigned to the heliostats that are individually controlled. I would note that the reheater has been eliminated in the Ashalim design because we learned it was no longer necessary. We simply have, for the steam turbine, steam generator, the steam generator coupled with a superheater, and it works quite well. Now let me show you what that looks like as if you were viewing it through the eyes of the Sphinx. What you're seeing here is an image of the solar boiler management system in infrared that tells us its performance. We can look at, in the middle, in the yellow, I mentioned if it's a cross section and you're looking straight at it, you can see on the bottom the flux kilowatts per square meter, and the top as if it's matching those three sections. And then the picture on the right is just an example of one of the weather stations and all the data that we're collecting. And that information is always presented to us in the control room, both locally and in the central control room. And maybe for a little more detail, here we go. This is how we use laser scans, and they coordinate to deliver flux to receiver. We're using laser in both the initial calibration and then we do continuous calibration. The GPS is used in the positioning. So we have this coordinated field of heliostats that's delivering flux to the receiver that enables the system to achieve the required temperature and pressure levels as in accordance with the specifications. And I mentioned the Sphinx software enables automatic continuous calibration for those heliostats when they are not in tracking mode. So this is one of the ways in which we maintain the performance of the system on a day in and day out basis. The receiver itself, this is a view of this receiver that we had at our SEDEC facility. So this is a different design, but you have a sense of how it's performing here, which is an image just looking at flux and how it's being monitored in real time, continuous optimization. And I'll talk about the tube coatings here in just a moment. So we'll talk a little bit about the wireless solar field network. In the right-hand side, you can see the power, and there were power cables and communication cables that were laid across the solar field. Here we have the tower in the back, and in the back you can also, if this were closer, if you had it in your face, you could see it in more detail. But nonetheless, that gives you a sense of the challenges and how can we reduce costs. Well, we have put in place now the wireless solar field network, and that implementation is first at the Ashalim project. So here at Ashalim, we have 50,600 heliostats, so 50600 heliostats that are positioned in just over its 3.15 square kilometer field, and they communicate wirelessly with the Sphinx. And that wireless system enables us to reduce cabling by as much as 85% in the solar field. And that has the benefit of both reducing costs and accelerating the construction schedule. And if you look down below off to the lower right, what you'll see is a pole, and that is an access point. And so they're in groups in each cell, and there's an access point that, again, is connected through an optic fiber back to the central control. But all the heliostats themselves are controlled wirelessly. On here, if you look, that's the PV panel and the wireless heliostat wireless control that are connected with a supercapacitor to provide power. And this represents the first deployment of this technology. It was tested independently and validated at our SEDEC, which is the Solar Energy Development Center, which is a fully operational sun-to-steam solar facility that we use to test equipment, materials, and procedures, as well as construction and operating methods. Receiver coatings, again, this is showing you the receiver coating at Ivanpah. But the main point is that we have evolved beyond the originally the Pyromark, which is sort of an industry standard, and have developed proprietary coatings. And those coatings enable us to do two things. One is to actually increase the overall performance because it's absorbed more efficient at absorbing sunlight. And secondly, the frequency between when you might be expected to recoat on the tubes goes from 2.2 to 3 years to 8 to 10 years. Again, this is another way of trying to find ways of squeezing costs out in the system. This tower, by the way, was 140 meters, which is 1 meter tall than the Great Pyramid of Egypt. And when I show you the Ashlim Tower, you'll see that it is 240 meters tall. So different designs, but these coatings, again, it's in 3 sections. I mentioned the receiver, superheater, and reheater. Temperatures obviously in excess of 538 degrees Celsius and 160 bar. On top of this project, there was a tune mass damper, which is a series of weights that shift. Because in California, the concern is not earthquakes, because the structure is very safe, but rather the wind loading that occurs at the top. So thinking and planning for that was one of the engineering challenges. And so this is just, again, the SEDEC, where we are showing the molten salt receiver. We have molten salt storage tanks, and this has been in operation now for about 1.5 years. So we continue, obviously, to make sure we fully understand its interaction and performance before we introduce it into the marketplace. But it has been qualified in South Africa under a bid, and we're hoping that we hear something sometime fairly soon about molten salt, which would be a project with 9 hours of integrated storage. We actually look to match the appropriate technology to the climate conditions. And so in the case of China, I believe that the first configuration is a hybrid, which is a steam receiver with molten salt and a heat exchanger on the tanks. But we anticipate over time that may very well transition to full molten salt. But again, when you're financing projects, it's important to take incremental risk and to prove out each project so that you demonstrate and to manage it appropriately. So let me just show you a couple of pictures here. First, to talk about the Ashlim project, which is 120 megawatts in the Negev Desert. It has a 25-year PPA. The land is 3.15 square kilometers, and there are over 50,000 of our new design, the Heliostat version 2.4, that has just over 1 million total square meters of surface area. Tower height at 240 meters. This project does allow for natural gas. And though I didn't mention it yesterday, it's probably worth when we talk about. Natural gas here is used to maintain system temperatures and pressures overnight so that we can see very rapid startup. In fact, at Ivanpah, they went from initial startup that would took a couple hours as they learned the system to today we are delivering energy to the grid within 20 to 25 minutes of sunup. That's how quickly we can do that by maintaining it. But I would also point out that the use of natural gas is the functional equivalent of drawing electricity from the grid for heat tracing to keep the pipes warm. So it's very similar. So as you think about that, there's nothing unusual. But where you have access to gas, it's less expensive. And if you can produce power from that, if it's allowed, it means better asset utilization, which means lower cost and better benefit for consumers. So where it's allowed, it makes sense, and we try and design what's appropriate for the rules in those markets. So here I'll show you a little bit more up close. Tricky. It's not touchable. Yeah, much easier. Thanks. So here you can see the tower under construction. Just a couple notes here. the government made this available as is. And when I say as is, this location was previously used for military training and target practice. So one of the first things we had to do when we had this plot was to check for and make sure that all of the unexploded ammunition was cleared from the site. We also had that in California on a project that it was used for tank training during World War II. And so it seems that sometimes you'd be surprised what you might find out in the desert. Once that was done, a couple of other interesting features here. If you look a little closer, you'll see that tower that's being constructed. It will be moved over into the foundation as it's completed, very slowly. If you think of how they move the space shuttle or one of the rockets, from NASA for a launch, that will move down and into that place. But there is also a river, essentially small, halfway between a river and a stream that runs through this property. And we also have historic trees that have to be protected, and they're literally right next to trees that must be protected there and out in the field, and you can see that being assembled. So it's an interesting opportunity, but again, it's that software that allows us to accommodate and work through these constraints, which are fairly typical. And again, another benefit is we can develop projects and help build them in areas that otherwise may be overlooked. Occasional rain that would require something different. So we think that is a benefit. Of course, I should say, the reason that we're here talking about these technologies is we're a technology company. And these solutions are available through our joint venture here in China with our partner, Shanghai Electric. So we encourage people who are interested to come and talk to Yvonne Huang, who is our head of China here. But nonetheless, that's what we're looking to do, is to bring these solutions to the market to ensure a successful pilot program. This is just a different view. Across the way is a small agricultural area that's been around there, and you can get a sense of the scale of this project. And again, it's an unusual layout and asymmetric design. And then finally, yesterday I mentioned the guidebook. I wanted to make sure that you knew you can download it for free. It's 124 pages, both in English and Chinese. And this talks about the value of CSP and the methodologies and where it's being worked. So if you go to brightsourceenergy.com, and I think we also have a brightsourceenergy.cn website as well. And a lot of this information is there as well. So I have a few minutes, I think, for questions and answers. I'll provide the answers, hopefully, and you have the questions. So thank you. Any questions?
你好，Desmond.
I'm sorry.
你可以声音大一点。
我想问一下，就是你们好像刚看你们介绍的是
中文。
就是2014年那个用那个水工资代替这个熔岩，就是你们认为这个哪一个工资是更有优势？谢谢。
So in 2014, we installed a molten salt receiver in storage tanks. That's based on our view that we look to provide the technology that makes the most sense. There are advantages to having steam. It's well known, it's well understood, it can be managed, and we have designed systems that integrate efficiently with molten salt storage. A molten salt and integrated molten salt storage is more efficient by a few percentage points, but that has to be weighed against, again, the climatic conditions. But we try and make the recommendation that makes the most sense. What I would point out is it was unfortunate in that in California, when the utilities were issuing their request for proposals, they only considered first cost. which at that time in 2007, when we were bidding these projects, the cost was essentially, would be more expensive if you added storage. There was no value placed on storage when California issued its first request for proposal. No one was anticipating the challenges of high penetration of PV, of the grid reliability concerns, and so you would have seen storage there. But I think it's fair to say anything going forward always incorporates storage. But I would say we're agnostic, meaning we're not biased of one to the other. They both can work and can work quite well, and I think that's been proven out over time in many different places. Yes, sir.
Good morning, sir.
Good morning.
Congrats for your exposition. My name is Javier Bellato from San Jose. And I would like to know, because you know, when you design your solar field, you have to balance two antagonic concepts, which are the size of the panels and, of course, the DCS. Okay? If you install so very huge mirrors, you have the risk to have a not very good accurate concentration in the receiver. Okay, they will be more affected by the wind, of course. But if you build more mirrors, more heliostats, but with a less size, smaller, then you have to increase your DCS. Okay? Then how can you balance these two concepts to optimize the solar field and at the same time the DCS? Thank you.
Sure. Good question. We're optimizing more than just the DCS and the size. We're taking into account fabrication, manufacturing, logistics, shipping costs, ease of installation. We also, when it comes to maintenance, there's also, you reduce risk by having more heliostats. If we have a field of, say, 60,000 heliostats, at any given point in time, there may be some communication issues with a very small percent. So you reduce the risk of having more availability by having essentially, it's just N-1 contingency planning, fewer. The second is, this comes from experience. We have been testing different sizes at SEDEC for many years. And if you were to watch and look at a video construction, one of the things you'll find during installation is when we have the cranes that lower these down. A smaller heliostat allows one-man operator to use that crane. Additionally, a smaller crew on the ground can take that. But you also need to think about wind loading, because as you're moving that, the wind will push that, and a big heliostat is like a giant sail on a ship, and it can be very dangerous. You also have harmonics associated with motors that are turning heavier loads, and the necessary equipment. So I think what you'll see is, it's our view, is that a moderate-sized heliostat that is accessible from the ground for access and maintenance, coupled with a foundation system that minimizes impacts, we think is a good way to go. Other people have different opinions, and that's okay too. Yeah.
谢谢啊，咱们时间。我还有个问题请教一下，就是刚才您讲到的那个吸热器的高温涂层，你在那个18000的项目中用的是那个 PureMark 的涂层。据我们了解 ，PureMark 涂层它的热吸收性能确实非常好，但是它的热发射的损失也是非常高的。那么你们现在在那个阿蒂姆的那个新的电站过程中使用的 DSE 的涂层，是否就是你考虑到这个性能？
Okay, I'm sorry, I had a problem again with this. Could you just repeat the first part of the question one more time? My apologies.
OK，就是您刚才讲到的高温涂层，吸热器的高温涂层，在10000帕的项目中用的是 PureMark 的涂层，它的吸收性能确实比较高，但是据我们所了解的，它的热发热损失也是非常高的。 在你的那个阿利姆的那个新的项目中用的 BID 的涂层，是否考虑到了它的热发热损失提升，就是所以导致它的性能的一个提升？就是你可以描述一下你新的涂层的一个吸收和发热性能吗？谢谢。
I cannot describe it specifically in detail, but what I can say is we recognize that issue, which is why we developed our own set of proprietary coatings that we make available. It's those coatings that actually improve the absorption and minimize some of that heat loss. So we're looking at an alternative approach that, again, squeezes some efficiency out of the system for improved performance. I don't want to also overlook the importance of the labor cost associated with repainting the tubes or the tube coatings every 2 to 3 years compared to every 8 to 10 years. That's also one of the other benefits that we think about when we looked at switching to that type. But there was a lot of testing of that coating mix that was done over time. We had experts, chemical experts I know, that came in that we worked with to develop that and filed patents on that.
那个咱们已经严重超时了啊！刚才就是最后一个。
Okay, I'll make myself available after if there are other questions. Thank you.